Welcome to the Explainer. I am your host, and today we are stepping straight into the laboratory to engineer the absolute perfect exam strategy. We are looking deep into the Cambridge Mathematics past papers, specifically focusing on the 0580 syllabus. But listen, if you are sitting there tackling the 0606, 4004, 4037, or 4040, do not go anywhere, because these universal examiner strategies absolutely apply to you too. Here is the harsh reality we need to face right now. Every single year, literally thousands of students walk into that exam hall, their hearts are pounding, they sit down, open the paper, and they totally misinterpret what the examiner actually wants from them. Let me introduce you to two classic student profiles I see literally all the time. First, we have Alex. Now, Alex is an overloader. Alex reads a question and writes down every single mathematical fact he has ever memorized, just throwing raw data at the page with absolutely no structured analysis. It's just a huge mess of numbers with no clear direction whatsoever. And then we have Sam. Sam is a rusher. Sam sees a number, immediately grabs a calculator, and completely misses the crucial command word requirements. Sam loses easy, foundational marks just because he didn't answer the specific question the examiner asked. If you are writing your papers like Alex or Sam, you are leaving precious, grade-defining marks on the table, and your paper is going to come back covered in red ink. But today, right here, we are stepping in as your personal exam strategist. We are going to completely transform those red marks into green check marks by unlocking the exact secrets hidden right inside these real assessment papers.
To master this, we're going to climb what I call our mathematics skill tree. We'll start by tackling percentages and depreciation, move right into the art of estimation, scale things up with standard form, and finally, we'll face our final boss battle, visualizing set theory.
All right, let's unlock Node 1, Mastering Percentages and Depreciation.
Okay, let's dive into this. Examiners aren't just testing if you know what a percent actually is. They want to see if you can track a value as it dynamically changes over time. When Alex sees a percentage question, he instantly tries to calculate a flat percentage and just subtracts it over and over. When Sam sees it, he rushes and skips reading the time frame entirely. Look at this exact question pulled straight from Assessment 2. A boat loses 15% of its value each year. How long will it take for its value to halve? Now, this right here is a beautiful, classic example of a compound depreciation problem. Notice anything missing? There is no starting dollar amount given. This is exactly where Sam usually panics. He literally says, how on earth can I find the value if I don't know what the boat costs in the first place? But top-tier students? They use multipliers. The actual starting price doesn't matter at all. The mathematical relationship is the only thing that matters. You are looking for a time frame where the compound multiplier drops the initial state below 50%.
Here's the exact step-by-step logic that prevents you from freezing up on complex word problems like this one. Step 1. Treat the starting value of the boat as 100% or simply the number 1. Step 2 is the magic key to the whole thing. Apply a 0.85 multiplier. Now, why 0.85? Because 100% minus that 15% loss leaves you with exactly 85% of the value at the end of every single year. Expressed as a decimal, that is 0.85. Step 3. Continue applying this multiplier for consecutive years until the final result drops below 50%, or 0.5. So mathematically speaking, we are solving for n in the inequality 1 multiplied by 0.85 to the power of n is less than 0.5. If you grab your calculator and test the numbers, 0.85 to the power of 4 is roughly 0.522. Almost there, but not quite halved yet. But 0.85 to the power of 5 is approximately 0.443. Boom! It drops below half in the 5th year. By structuring your answers systematically like this, you absolutely guarantee full marks. Now, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Module 2, the art of estimation. You know, Cambridge exams demand a lot more than just exact calculations. They demand strategic rounding. Whenever you round a number, you introduce a tiny distortion into the universe, and the examiner specifically wants to see if you can quantify exactly how much distortion you've just introduced. Let's look at this race time question directly from Assessment 4. A girl runs a race in 14.2 seconds. If she rounds her time down to 14 seconds, what is her error as a percentage of her actual time? Think about how our friend Alex approaches this. He sees 14.2 and 14, he subtracts them to get 0.2, and he just writes 0.2% as his final answer. He has the raw facts, but absolutely zero analysis of the command words. The question didn't ask for the raw difference, it asked for the error as a percentage of our actual time. Now, what's really interesting about this slide is how it visually contrasts the raw data with the student's applied estimation. Look at the exact time, it's 14.2 seconds. The rounded time is 14.0 seconds. The absolute error, meaning the raw mathematical difference, is exactly 0.2 seconds. But Sam, who always rushes, might take that 0.2 seconds and divide it by the rounded number, the 14, to find his percentage. That is a completely fatal error in an exam setting. You must always anchor your percentage error to the actual exact starting value. If you don't, your entire calculation crumbles.
And this is exactly why examiners love to test this specific cognitive leap in your accuracy. Percentage error is formally defined as the mathematical difference between an exact and rounded value, divided by the exact value expressed as a percentage. So let's engineer the perfect structured response here using the PL framework. Point. The absolute error is 14.2 minus 14, which equals 0.2. Evidence. We divide this error by the exact time, so that's 0.2 divided by 14.2. Explanation. When you run that, it gives us a raw decimal of approximately 0.01408. Link. Finally, we multiply by 100 to express it as a percentage, giving us a highly accurate final answer of 1.41% to 3 significant figures. That is how you lock in top marks.
Let's step into Module 3, Scaling Data with Standard Form.
Before we tackle this massive number, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's look at this. When we deal with astrophysics, microscopic biology, or massive national economies, standard numbers become a huge liability. They are incredibly bulky, they are highly prone to miscopying, and they are an absolute nightmare to punch into a calculator when you're sweating under time pressure. Look at this monstrous number straight from Assessment 5, 778 million kilometers. This is the staggering distance from the Sun to Jupiter. Just imagine trying to multiply or divide this raw, massive distance while rushing. If you miss just one single zero, your entire calculation is thrown off by a factor of 10, and your examiner will mercilessly dock all your accuracy marks. So, how do we extract the core trend from this massive number and write it elegantly?
So the crucial point here is that mastering standard form notation is your best defense. The standard form equivalent is 7.78 times 10 to the power of 8 kilometers. By smoothly moving the decimal point 8 places to the left, we create a manageable number between 1 and 10, and we multiply it by a power of 10. Mastering this doesn't just save you precious time, it completely prevents those heartbreaking zero-counting errors that destroy grades. It takes the clumsy and makes it brilliantly precise. But listen, the exam doesn't just want you to translate standard form, it wants you to operate dynamically with it.
Let's see if you can spot the massive trap in how most students approach this dual-layered calculation. If light travels at 3 times 10 to the power of 8 meters per second, calculate the number of minutes it takes for sunlight to reach Jupiter. Now this is a heavy question. It requires index laws, physics formulas, and unit conversion all at once. A rushing student, our classic Sam, will just take the distance, 7.78 times 10 to the power of 8, and divide it right away by the speed, 3 times 10 to the power of 8, and proudly write down done. It takes 2.59 minutes. But Sam completely missed the trick. Sam fell face first into the trap. The speed is given in meters per second, but our distance is in kilometers.
Let's carefully walk through the exact calculation path you need to take, proving once and for all that a systematic approach will always defeat an overwhelming physics-style math problem. Step 1. Standardize your units. We absolutely must convert 7.78 times 10 to the power of 8 kilometers into meters by multiplying by 1,000 or 10 to the power of 3. That gives us a true workable distance of 7.78 times 10 to the power of 11 meters. Step 2. Divide distance by speed. We know distance over speed equals time. So that's 7.78 times 10 to the power of 11 divided by 3 times 10 to the power of 8. Using our index laws, we simply subtract the powers. This gives us roughly 2.593 times 10 to the power of 3 seconds, which is 2,593 seconds. Step 3. Read the command word. It asked for minutes, not seconds, so divide by 60. 2,593 divided by 60 gives us exactly 43.2 minutes. Boom, perfect execution.
And finally, we arrive at Module 4, Visualizing Set Theory.
Listen,
Navigating abstract logic is the ultimate separator between average students and top-tier A-star candidates. When you are hit with paragraphs of overlapping data, trying to hold it all in your working memory is a guaranteed way to fail. You have to translate those words into a clear visual blueprint. Let's display this incredibly tricky mixed farming data set from Assessment 8 to demonstrate exactly how confusing word problems are before you start visualizing them mathematically. The problem states there are 77 farms altogether. 19 farms keep exclusively goats, 8 keep exclusively cattle, 13 keep exclusively sheep. Now, if you just look at this table, there are huge glaring gaps. We don't know the totals. We don't know the overlaps yet. Alex would just try to blindly add these numbers up and wonder why on earth they don't equal 77. The answer, my friends, lies in the intersections.
Now let's list the overlapping intersections clearly. The problem text continues, 13 farms keep both goats and cattle, 28 keep both cattle and sheep, 8 keep both goats and sheep, and this brilliantly illustrates why we absolutely must build a Venn diagram piece by piece. These both categories are incredibly sneaky because they include farms that might actually keep all 3 animals. If you just write a flat 13 in the goat and cattle intersection on your diagram, you are actually double counting the farms that also have sheep. It's a massive pitfall. You always have to work your logic from the inside out.
And here it is, the ultimate set notation boss battle question. From 77 total farms, calculate the value of n of G intersection C intersection S. This is asking you to mathematically find the triple intersection, the exact number of farms that keep all 3 animals at the same time. Let's engineer the equation step by step, nice and easy. Let the unknown triple intersection, right in the middle, be x. That means the goat and cattle only area is 13 minus x. The cattle and sheep only area is 28 minus x. The goats and sheep only area is 8 minus x. Now, if you add up the exclusive farms we knew earlier, 19, 8, and 13, plus these 3 new expressions, plus x in the very middle, all of that must perfectly equal the grand total of 77. So the equation is 19 plus 8 plus 13 minus x plus 28 minus x plus 8 minus x plus x equals 77. Take a breath and combine the numbers. You get 89 minus 2x equals 77. Move the 77 over, and you get 2x equals 12. Therefore, x equals 6. There are exactly 6 farms that keep all 3 animals. That right there is how you decode, visualize, and execute an A-star answer.
Okay, let's synthesize all these isolated mathematical nodes into your final rapid-fire exam success blueprint. We have seen exactly how skipping steps, ignoring units, and failing to visualize data completely destroys your mark potential. You can't just wing it. You need a system. The 3 rules that guarantee top marks are: 1. Command word decoding. Always check if you need percentages, minutes, or specific significant figures. 2. Peel framework application. Structure your math with clear points, evidence, explanations, and links to the final answer. And 3. The time management matrix. Please, do not spend 10 minutes sweating over a 2-mark question.
Take a quick look at this foundational conversion table from Assessment 2, knowing instantly, without even touching a calculator, that 3/5, 0.60, and 60% is the absolute baseline for securing top marks. If you are stumbling and hesitating on these basic conversions, the complex problems we just did will completely overwhelm you. You must build your foundational fluency so that your precious mental energy is 100% reserved for the complex problem-solving and deep analysis we just worked through together. Seamless fluency across formats isn't a bonus, it is your required baseline.
I want to leave you with this core mantra today, completely reinforcing that an exam paper isn't just about throwing raw facts at a page, but structured analytical execution. Engineer the perfect DNA of an answer. Evidence plus analysis equals A-star. You cannot just rely on your gut feeling or half-memorized formulas. You must vividly show the examiner the exact logical path you took to get there. Every single line of your working out is a piece of hard evidence. Every correct formula applied is your analysis. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Think back to Assessment 1 for a second, where we had to decide if a rod's length is rational or irrational. The examiner is literally asking you to categorize and prove your stance. So I have to ask you, are you simply memorizing irrational numbers and just hoping for the best? Or are you actively engineering a highly rational, structured strategy for your next exam? Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.